Okay, so it's my pleasure to introduce our next speaker, Ian DesJardin from the University of Maryland, College Park. He did 2 practicums at the Princeton Plasma Physics Laboratory.
Thank you. So today I'm going to talk about multifluid space plasma simulation. It's kind of a wordy title. Sorry about that. What we're actually talking about is space debris. So if you're unfamiliar, there's a lot of things that humans have put in the orbit of the Earth. This is a particular pictorial representation of that. This is the official United States government catalog, and each dot represents a thing in orbit. And the color of the dot indicates whether it's functioning or not functioning or its category. And so debris is defined as anything that humans have put up there that either no longer functions or is fragments or is a used rocket body or things like that. And frighteningly, with a lot of it, we don't know where it is. So this is a study by this ground observatory. And the green dots indicate things that this ground observatory saw that were not in the official government catalog. And you can see there's a number of things. And what these things are is they are debris fragments. So, and this, if in case it's not obvious, the Earth is in the center here. So when you launch a satellite, sometimes you want to send them to this region called the geobelt. And so you'll launch them on this transfer orbit, and then you'll have parts of the rocket that are used up and no longer used, and they just kind of spread out along this transfer orbit, and then they stay there kind of in perpetuity. And if it did nothing, no one would care about it, but the problem is it runs into things. So what this is a picture of the Space Shuttle Challenger's front window during a servicing window. And this here is 1 millimeter in length scale. So this is a small piece of debris, basically hit the windshield. And because everything is going in at least 17,000 miles per hour in orbit, small things cause very energetic collisions. And currently, what I've just shown you is an instance where large debris is not all tracked, but fundamentally we can't track small debris. These are the ways that traditionally people have tracked space debris. So we use things, big radar stations like Goldstone, or these Baker-Nunn cameras, which are telescopes that are specially designed for tracking objects in space. And for debris in particular, one of the most successful ways of mapping it is actually just putting experimental plates on the end of space stations and then counting how many times they get hit. And that's how a lot of the debris population density is inferred. And these 2 methods are kind of, they're very much at the technical limit of, we've built the most powerful version of them we can. So radars, they have 1/r⁴ losses. They're limited by transmission power, and we've built some of the biggest radars we can. And so they can't see anything smaller than about 2 centimeters. And telescopes are fundamentally limited by optical brightness and atmospheric aberration, and so they have an even higher size resolution. So all this is to say is we need a new method of detecting space debris. And so my research has been on modeling a new method which uses a fundamentally new mechanism of detection. And so this method is using the native space plasma that exists around the Earth. So, Earth exists in a vacuum, kind of, but it also gets hit by something called the solar wind, which emanates from the sun. And it's a very diffuse plasma. So it's basically bits of the sun that fly away. And they get trapped in the magnetic field, and they form this thin layer of plasma that surrounds the Earth. And it's higher in other places and lower in other places, and it has this very complicated geometry, but we don't care too much for this talk. And things that flow in this are going to interact with it. So this is a laboratory experiment that was published in Physical Review a couple years ago. This dust flow is a dusty plasma flow. So the dust there is a tracer particle so you can see what's happening. And it's flowing from right to left. And this wire is a stand-in for a piece of debris or something that's in the flow. And what happens is these waves will develop that flow upstream. And these waves we're going to call solitons. And they're a very special type of wave for a lot of reasons I don't have time to go into. But the question is, can we see these solitons? Because in this picture, for example, if we wanted to look for the wire, that would be hard. It's not visibly obvious, but the solitons are. So because they're larger than the debris that would create them, could we see them by proxy? So what are the physics that goes into this? So first, there's this debris, and this debris is going to accumulate some free charge on it. This is the interaction, part of the interaction with the space plasma. So free electrons and ions will hit the surface, and some surface charge will develop. This surface charge will develop a boundary layer near the debris, which we call the plasma sheath. And that plasma sheath is immersed in a flow, and that sheath is going to push on the plasma through electric forces and create these complicated structures. And so these are some publications on this. And so this is CSGF, obviously. So why do we need computing in all of this? So I'm sure every field has this basic paradigm. There's something we're interested in studying. We can measure it, but there's only going to be measurement error. There's theory, but if the theory is simple, or if it's at all complex, then we need a computer to solve it. And in this field in particular, there's an added complication, which is we want to measure these things in space. We want to look for these solitons. But as I'm going to show you, they're only created in certain places. They need a special set of circumstances to make them happen. And so we need to predict where they're going to happen and how big they're going to be so we can design an instrument to view it. So computing has a very important role to play in this. So this is the simplified model that people use. It's called the KdV equation. And there's been a lot of thought put into making a lot of assumptions about the space plasma. And in this case, what you do is you put in the source on the right-hand side, and then you get an equation for how the waves develop. And so this is some of the solutions that you get, and this is the simplified 1D model. So there's two solitons here, and they're these each hump here is an individual soliton, and they have this property that they will move through each other while maintaining their stability. And so you can imagine, as a sensing technique, they're going to exist for long periods of time, and they're going to be stable in a noisy environment when they're interacting with other things that might exist there. So that's part of why they're a very attractive thing. There was a couple previous talks where people talked about phonons in semiconductor materials. And I wanted to just draw a quick parallel, because I hadn't heard of that before the other day, and I was digging into it. So as I understand it, phonons they're this lattice vibration, but you can treat it as a quasi-particle. And so it has this interesting mathematical behavior because of a bulk motion particle duality. And solitons are similar in that respect, where they're a collection of Fourier waves that stack on top of each other, but they do it in this stable way. So you can treat this as one object, even though it's actually many things masquerading under one object. And so soliton generation, it only happens in a very specific range of Mach numbers. So Mach number is defined as the flow speed, or the speed of the object, defined by the local sound speed. And because we're in a collisionless plasma, it's not the traditional sound speed of air. It's this different speed called the ion acoustic velocity. And I'm glossing over some details here, but that velocity is basically determined by just the electron temperature. And what I'm showing you on the right here is a global model of the space plasma. And this is at 342 kilometers altitude, which is pretty close to where a lot of satellites operate. And you can see that this temperature varies by about an order of magnitude. It's hottest on the day side, so you can see the sun here. And then there's a convection pattern, and so that's why you get this this north-south variation here, and it moves with the day-night cycle. For example, so for the speed of sound on Earth also depends on the air temperature, but the air temperature doesn't go from 450 to 2500 Kelvin. It stays, it stays within about 100 degrees, right? So there's much more variation in the ion acoustic speed. And because of that, even for something which moves the same speed, its Mach number varies wildly as it goes around the Earth. And in the development of this, of all of this theory, people have identified basically 3 behaviors that happen. So you either have small linear waves generated, or most interesting in this range here, you get something called precursor solitons, or above the supercritical Mach number, you get pin solitons. This is what the precursor solitons look like. So there's a bit of debris that's fixed at here chi equals 128, and there's these density waves that propagate upstream. And upstream here means that if I'm a space station and there's a piece of debris coming at me, there's going to be waves emanating from the debris before it hits me. So this type of situation would be really, really attractive for early warning systems. And then above the supercritical, what happens is the soliton stays with the debris. And in this model of the FKdV equation, people have proposed these as limits, and A is, it's an integral over the size of the debris. But here's the thing, is there's a lot of assumptions that go into this, and it's not really been tested computationally, especially in a plasma physics context. And so that's one of the things we did with this fellowship. And so what we did is we solved the full multifluid equations, which it's not this. It's mass, momentum, and energy for both ions and electrons, and then the full Maxwell's equations. So we're not making any assumptions about anything that goes into deriving this. And then we run a lot of simulations, and having HPC helps if you want to bang out 150 variations of basically the same thing. And this is the result you get. So the dots here indicate what type of behavior we observe. And then this black line indicates the theory that I just showed you. And yeah, you can see that they don't agree. And so this has been super, super useful because we discovered this disagreement with computation, and we've actually been able to go through and derive some new theory which does agree with this data. And so if you want to read more about this, there'll be an upcoming journal paper with the same title as this talk. But anyways, I think that's about all I have time for. So I'll summarize by just saying my future is I'm going to defend my thesis this summer, and then I'll be starting at NASA Goddard in the fall. And of course, thank you to everyone along the way. A special shout out to the Jekyll team at PPPL because I used their code to do this. Also my advisor, Christine, the whole Krell staff, everyone here who's been happy to talk about this for years and years. So thank you so much.